Okay, I think we have pretty much everyone. So without further ado, I want you guys to keep your eye out. So if you look here, I want to invite Aditya Dawan, and he's going to be doing a presentation that will be very interesting for people like me who have. Oh, sorry about that. 1 second. Sorry about that, just had some technical difficulties, but I think we're all good now. So for people like me who have really messy handwriting, this workshop will be super interesting to you guys. So I would like to invite Aditya Dawan to do his presentation on handwritten digit classification. Sounds fancy.
Yeah, sure. So let's get this party started. I'll just share my screen real quick. Can everyone see, or is it good for everyone? Okay, let's go. Yes, so hey guys, hope you're all having a fantastic first day of winter break, and welcome to the 0 to 1 AI workshop here at Innovire. If you don't know me, my name is Aditya Dawan, and I'm a 15-year-old who is super into artificial intelligence and really anything about technology. Over the past 6 months, I've had the amazing opportunity to build AI systems for a company called Actionable.co as a machine learning specialist, helping me to see firsthand what these crazy new technologies are really capable of. I'm also an alumnus at the Knowledge Society, a community of people looking to change the world and solve important global problems using exponential technologies, things like blockchain, gene editing, and more. My time there inspired me to start Krista, a company I'm building to help improve student productivity by taking into account their daily energy levels. And really, if my experience at all of these amazing places with all of these smart people have taught me anything, it's this. There are a lot of problems out there, and it's our duty as humans to work to solve them. And for any given problem, there are near infinite numbers of solutions, near infinite numbers of tools that you can use to solve the end issue. If you're working to solve poverty, for example, you might use blockchain to keep better track of funds. Or you might realize that the root cause of poverty actually lies in manufacturing, and you might see how 3D printing could be used to your advantage here. In any case, the end idea is always the same. The more tools you have to solve a problem, and the better you know how to use those tools, the more likely you are to make an impact and get rid of the issue in the first place. And really, that's what artificial intelligence is. Another tool in the toolbox, one that's growing so rapidly that it's become a huge part in solving many global problems. For example, farmers no longer have to spend and use huge amounts of weedicides. AI systems can use object detection to spray chemicals accurately and precisely. In fact, these AI systems have gotten so accurate that some can even predict how likely you are to develop strokes and cardiac disease before they can even happen. And to me, that's just nuts. Considering that this field almost didn't exist just 2 decades ago, it's insane to see just how far we've come. Now, it's possible to learn and become skilled at AI from the comfort of your own home. And in fact, by the end of the next 3 days, you yourself will have developed an AI solution, one that can help to solve important global problems. During this workshop, we will be going 0 to 1 on all things artificial intelligence. From classifying handwritten digits to predicting the price of stock, you'll go from having little to no understanding of artificial intelligence to presenting a well thought out AI solution to a problem that you are passionate about. What's incredible is that these algorithms are everywhere around you. Chances are that many of you signed up from this event for our Instagram. And if so, that post was recommended to you by artificial intelligence. If you used your phone this morning to scroll through YouTube or Twitter, then you have also encountered an AI algorithm. If you really think about it, AI seems kind of black box at times. How does this all even work? Is AI just something that you slap onto a product or problem to magically make it better? Well, no. In reality, AI is actually really, really simple. It tries to find the relationship between two things, an input and an output. For example, let's say that you wanted to make an AI to classify whether a picture was a dog or a cat. Pretty simple, right? I mean, for us, we can just kind of look at the picture and tell what it is. But for our algorithm, this process is a lot more difficult. And I mean absurdly difficult. So you give the AI an input, in this case, a picture of a dog or a cat, and then you give it an output, which is a label, either a cat or a dog. And over time, as you start giving the AI more and more examples, more and more data, the algorithm starts making tiny little changes to itself. It starts making little corrections, almost like it's learning from its past mistakes. Until after a while, something clicks and it realizes that, hey, this is a cat and this is a dog. Now, how exactly did this happen? How is it that our AI was able to come to the understanding that certain images represent cats and others represent dogs? The way AI is able to do this is all thanks to the magic of one small unit, known as a perceptron. And these units are pretty simple. They take an input, transform it in some random way, and then they return an output. For example, if you gave a particular perceptron 20 as an input, the perceptron might take that in, multiply it by 2, and return 40 as an output. And really, AI algorithms are just based off of hundreds and thousands of these small units, all put together into something known as a neural network. But not like this. This is way too random and complicated to make any sense. Instead, these perceptrons are organized tightly and neatly into layers, the input and output layers, and the hidden layers. Really, neural networks are just like giant perceptrons. They take in some value through the input layer, transform it through the hidden layers, and return it to the output layer. So, going back to our dog or cat photos, we wanted to pass in a picture to our input layers, transform this image in some way through the hidden layers, and then return whether this picture was a dog or a cat in the output layer. Now, right away, you might see a glaring problem here. How do we pass a picture into a network that's meant for numbers? That doesn't really make sense, right? Like, if you passed a picture into a perceptron, it can't just multiply the picture by 20. And even if it could, it's not like that would give you the output you needed. You can't really get dog or cat by multiplying 20 by a number, because that's just not how math works. You can't pass in 2, multiply by 20, and then get cat as your answer. So this is a rather interesting problem. We have the input as a picture and the output as a word, but the perceptron deals with only numbers. So, do any of you guys have any ideas or thoughts on how we can solve it? Type it in the chat. Anyone have any answers? If not, we can just continue on. Turn the photo into code. Interesting. It scans for features on a dog. That's also an interesting solution. Maybe you could calculate how long the dog is. Fascinating. Cool. Yeah, so these are all really interesting ideas. But I think that the solution might surprise you because it's really simple, as with all things in AI. So basically, we just need a way to turn all of our inputs and outputs into numbers that our neural network actually likes and can use. This is pretty simple for our output. Because we actually have two options, rather than saying dog or cat, we can just do something really simple. If we can say that the number is 0 if it's a cat and 1 for a dog. And even if we had more animals, for example, like if we added an emu and elephant out of nowhere, then we would simply add more numbers. The emu would be a 2 and the elephant would be a 3. So really, configuring the output to represent a number isn't that big of a problem because we can just link each number to a particular category. But what exactly do we do about our input data, which is the photo? Because really, we have to realize that a photo is really just a bunch of pixels, and each pixel holds a certain numeric value. For example, for a black and white image, the number values range from 0 to 255, where 0 represents black and 225 represents white. So technically, we could take a black and white picture, convert it into a bunch of pixels, turn these numbers into one giant row of numbers, and pass it in through our neural network. And here's an example of that. We have our image, we convert the pixels into one giant strip, which in this case has all the pixels in this particular image, and we pass it in through our neural network. Boom. And since this particular image is 16 by 12 pixels, in this row, we would have 192 inputs for the first layer, our network, instead of the 4 that you see here. So this would actually be 192, since that's the image size. So the problem really has been solved by a pretty simple solution. But wait, our images of dogs and cats aren't black and white. They're colored. So in this case, we have a slightly more complicated solution, but overall, still pretty simple. We know that the pixels of a color image can be broken down into 3 key channels: red, green, and blue, or RGB, if you will. So instead of having one number per pixel, now you have 3 numbers per pixel: one for the red value, one for the green value, and one for the blue value. You can do different things here. You might take the average of all 3, or you might just pass them all straight into the neural network. And really, as you can see here, we just have 3 different values. So it's like passing 3 different images into the neural network instead of just one. So as you can see, the blue layer has 4, 0, 2, 1, and the green and red layers both have different values. So for colored images, we basically just split the data into 3 different channels depending on RGB, or red, green, and blue. And this entire thing of changing the input and output data before passing it into our algorithm is known as data pre-processing. And it's an important part of all AI and machine learning applications. Regardless, we've solved the problem. Our inputs and outputs, or our X and Y values, to get very fancy with the math terminology here, can now be passed into the neural network. And we can even evaluate the accuracy and performance of our network using something called a loss function, which basically sees how far off the predicted output was from the actual output, almost like an inspector. So just to recap, the loss function just checks what your network predicted and compares that to what it should have predicted and finds the difference. So in this case, this is a random number, but it might return 0.089, almost like an inspector observing 2 different scenarios. Ideally, our accuracy would be really high, something like 99%, and our loss or error would be really, really low, maybe something like 0.01. Perfect. Now we can just give our network different input and output data, and the layers will just magically return whether each image is a cat or dog, 0 or 1. Right? Well, not exactly. See, there's still one more thing that our network actually has to do, and that is to learn. Right now, each perceptron in this network is just set to a random value. So if we take an image, convert it, and pass it into our network, we will just get some random gibberish. We need to find some way to change the weights in each perceptron every time we see new data. And this way, what we basically need to do is find the correct combination of perceptron values that will allow us to turn the input image into our desired output, which in this case is the cat. Now, there are multiple different ways that we could do this. We could do this randomly and hope by sheer luck, we'll get a combination of weights that actually give us what we want. But given the sheer number of perceptrons we have, sometimes up to millions and millions, this really isn't a smart idea, especially given that each perceptron can be set to really any value. Well, luckily, we have our error function that can help us solve this problem, and it can tell us how far off we are from our desired output. But how does that help us? It's not like knowing that our loss function was 2.43 is going to help us update the perceptrons in any meaningful way. Or is it? Let's run a little experiment. Let's say that our network is just one perceptron, our old friend x20. Now, this isn't actually possible since our image is like 1,000 by 1,000 pixels and we only have one node, but bear with me here. We pass our image in and we get a particular prediction, right? And in which case, it thinks that there is a 0.2 or 20% chance that this is a cat, and an 80% probability that this is a dog. We give this data to our inspector, the loss function, and he rightfully says that this makes absolutely no sense and returns an error of 10, because this is obviously a cat, and our network just said that there's 20% probability this is a cat and an 80% chance that this is a dog, which makes absolutely no sense. Okay, so let's just say that we randomly change this weight, just for the fun of it, to 19. Now what? Okay, slightly better this time. Now we have a 25% probability that this is a cat and 75% that it's a dog. Again, our inspector comes and gives us a 9 this time. So let's continue on. Choose random values for the weights and see what happens. Okay, cool. But how again does this help? Let's plot all of these values onto a graph. Do you guys notice something that might be helpful here? And if you're already familiar with AI, please don't respond. So drop your answers in the chat. How do you think this graph can help us to update our perceptrons? Cool. I mean, if you guys are kind of stumped, then we can always just continue on. Yeah, Ishita has a rather interesting suggestion. The higher the loss function, the higher the perceptron value. So this is actually exactly what we're going to be doing. So when our weight was 19, you might notice that the loss was extremely low. In fact, it appears that the further we go in this direction, the further we go left, reducing our weight by 1 at a time, the lower our loss gets. And really, this graph is almost like a mountain. We're trying to find the way to get down as fast as possible, a way to reduce the error as fast as possible. So we're finding the direction that has the steepest slope downwards. That's awesome. That means that we can make updates based on the slope of this line. If the loss function is going down as we reduce the weights, that means that we can take a step in that direction. And if it's going up, then we can just go in the opposite direction instead. And boom, we've kind of just solved the problem. Instead of just randomly updating the weights every single time, we can update the weights based on how they affect our loss function, based on how they affect our inspector. Now, in reality, the way that AI algorithms do this process of finding that steepest slope is a lot more complicated. For those of you familiar with calculus out there, we basically take the partial derivative of different points and use an algorithm called gradient descent to accomplish this. But the more advanced math is outside of the scope of this workshop. So for those of you super curious about this, I'll link some resources in the chat later on. But hey, we've just created an AI algorithm. Pat yourselves on the back. So let's quickly recap how an AI works. First, we need to take input and output data. We convert this data to numbers or to an acceptable format, and this is known as data preprocessing. Next, we create a neural network. We determine how large each layer will be, depending on what we want to do, and we set up our inspector to determine the effectiveness of our network. Step 3, we take the weights or parameters of our network over and over again, looking at how the loss function changes over time, and we change the weights based on this. We do this process thousands and thousands of times of updating the weights again and again and again, until finally we have a model that actually works. Finally, we test our model. We see how it does on data that it's never seen before. And to me, that's absolutely crazy. Some of the most complicated algorithms in the world, algorithms that can detect bacteria and asteroids, can literally be reduced down into just 4 key steps. And I think that's absolutely amazing. Now, some of you guys are probably a little bit confused or bored right now. So before we go in and actually build our first AI, let's have a quick Kahoot to see how much you guys understand. But before that, are there any questions? Any questions, thoughts, or concerns? Could you please explain that again? I'm not sure I fully understand how we can use the graphs. Sure. So I'll just go back to that real quick. Okay. So all we've done here is basically plot the loss of different perceptron values, right? So we set our perceptron to 19 one time, 20, 23, and 25. And we just plotted all of this on a graph. And what we're really doing is trying to see if there's any trend within these values. And there actually is a trend in this particular one. We see that when our loss function is, when the perceptron's value is lower, so 19, for example, the end loss also ends up being lower. When it's 19, it's around 9, 20, 10, 23, it falls around 15, and 25, it goes all the way to 22. So if we want to reduce our loss function, which is what we want to do since our AI is supposed to be more accurate, then we just need to find the perceptron value that has the absolute lowest loss. And we can see that the further we go left, the further this perceptron weight value is reduced, the lower our loss function becomes. So we can make a hypothesis based off of this and set our perceptron to lower and lower values. So that's really what this graph is doing, right? And ultimately, this entire process is handled automatically, right? And it's all done by gradient descent, but you don't actually have to worry about that right now because that's calculus. And nowadays, when you're programming AIs, all of these things are handled automatically. So all you need to do is build the AI itself. Cool. Let's go for another question. You can't use the slope formula because the slope isn't constant. Yeah, that's right. So we actually use the partial derivative for this instead. The reason I said slope was just because I didn't want to confuse anyone. And I didn't mean slope in the mathematical sense, more that you're just looking at the steepness of the line. So really it's partial derivatives, but we won't get into that right now. So what happens when the image goes into the neural network? So pretty simple. Let me just go back to that. There's a pretty cool diagram, I think. Yeah, so it's really just this, right? We take our image, we convert it into a bunch of pixels, and if the image is black and white, it's easier for us because 0 represents black and 255 represents white. So you might notice here that the values closer to 255 are like really bright, and the ones that are close to 0 are just basically black. So we convert it into a bunch of pixels, and it basically just becomes a grid, right? Then we take this grid, and we just make it into one giant row. So instead of having all of these numbers arranged in a grid format, we just put them one after the other, right? So 157, 153, 174, 168, all the way down to 218. And since it's just a string of numbers, basically, like a huge list of numbers, we can just pass it in through our neural network with no problems. Cool. So I hope that was helpful. So the loss function says if our output is accurate, yeah, that's basically what it does. It's basically like an inspector, right? So it just tells you that, hey, you know what? This is how far your output is from the actual prediction. Is it possible to make AI cook a variety of foods? So, like, you mean actual AIs to cook things? Because those I think exist, but they're very expensive, so I'm not sure how mainstream they would be. All right, cool. So, if there are any more questions, feel free to pop them in the chat. But for now, we'll be going on to our Kahoot. So I'll just quickly show you guys the link to that. Okay, so here's the game pin. Yeah, everyone join and let's get this party started. I'll wait for around 1 minute 30 seconds for everyone to just join. And please use your real name instead of spam names. Yeah, thank you. All right. Oh, wait, there's no Kahoot music. Did I mute the tab? Yeah, unfortunately, there's no Kahoot music. That's sad. David Chance. That's the name of our scientific teacher. No, I'm in grade 10 right now. That's for Ishita, who asked that question. Cool. It seems that we have 30 out of 45 participants. Okay, 33. Is there anyone who still has to join? I mean, there are still a lot of people who have to join, I'm guessing. Okay, 34. Is there anyone else who still needs to join, or can we start? Okay, one more person just joined. Yeah, I think we can just go for it at this point, right? Cool, let's start. All right, question 1. What does AI stand for? Okay, yeah, I was going to be really concerned if anyone answered like artificial insubordination or something. But yeah, cool. Right, nice. Rishi is in the lead. Okay, question 2. Multi-select. What is the purpose of AI? Okay. I think we can all agree it's definitely A. It's to become the Terminator and kill us all. Okay, cool. Almost all of you guys got it right. So for those of you who answered to get the lowest error and highest accuracy possible, that is true, but that's not the end purpose. That's more like what you have to do to get to the end purpose, right? The point of AI is to find the relationship between an input and output, and then depending on what kind of AI you're using, it's to produce an output based on that relationship, right? So to get the lowest error and highest accuracy, that's how the model learns. That's how it gains experience. It's not its overall purpose. But still pretty good try. And yes, it's obviously to become the Terminator, to the 2 people who answered that. Okay, Selena's in the lead. Perceptron takes input, transforms it by some operation, returns an output. And this transformation cannot be changed. Well, I think that's everyone, 32 people. 34, I'll just wait the extra 5 seconds. Okay, so most of you got it right, but a lot of you also got it wrong. So everything here is true, except this part. The transformation cannot be changed. Because if we remember, the way that networks learn is by changing the perceptron values, right? And they do this automatically through gradient descent and stuff. So actually, this is the only part that's false. But this part, perceptron takes an input, transforms it, returns output, that's true. Cool, let's see the leaderboard. Okay, Arush is on fire. Neural networks learn by slowly changing perceptron values based on how they affect the error function. This, I think, should be pretty obvious now that we've talked about it. We'll wait for 35 people. Okay, true. Yeah, I think everyone got this right, basically. So, nice. What is the goal of data preprocessing? Okay, so most of you guys got this right. These 2 answers, to convert data to numbers and to make sure our data size is smaller, is true, but those are more of side effects, right? The core point of data preprocessing is to convert it into an acceptable format, right? Converting data into numbers or making the data size smaller, those are ways you can preprocess data, but that's not the only way you can preprocess it. So the correct answer here would be green. All right, we have a slight change here. 2 more questions left. Neural networks are built on perceptrons, and the size of the layers is usually fixed. This should be pretty straightforward. Yeah. Oh, okay. So there's actually a pretty big disparity here. So I think the thing that probably threw most people off is the usually part. So yeah, the size of the layers in neural networks are usually fixed, right? The reason I added usually is because there's some new research nowadays where they're experimenting with having the size of the neural networks being altered dynamically based on the input output, which is pretty crazy, and it's a pretty new field of AI stuff. So understand how that kind of threw people off, but that is currently what we're doing. So cool. Good job to those of you who got it right. All right, second last question. How do we pass an image into a neural network? This we just talked about, so. Yeah, pretty much everyone got this right. Replace the image with non-image data. Yeah, but this answer is just way better. So, like, technically, yes, this is true, but also this one is literally exactly what we have to do. So yeah. All right, slight change, but we're still pretty stable. Last question. How can we pre-process categorical non-numerical output data? So if you guys are a little bit confused, how do we pre-process data that is in categories, such as dogs or cats, and if this data is like not a number, so if it's like a string, right? This one should be pretty straightforward because we talked about it. Okay, 3, 2, 1, and okay. Yeah, so this part is wrong. Converting each category to a list of numbers, that's what we do for pictures, remember? We convert the entire picture into a list. For categorical data, we just assign each category to a number. It's not an actual list, right? Because if it was a list, then you can't have 0, 1, and 2 all representing the same category because that just doesn't make sense. So the correct answer is blue here, but good try. All right, let's see the podium. All right, number 3, Zainab, 6 out of 8. Cool. Lisa, and first place. Arush, okay, cool. Nice, and also congratulations to the number 4 and 5 winners. All right, cool. So I hope you guys had fun with that Kahoot. And now it's time to actually start and build our first AI. Now, in the chat, you guys should have access to this Colab notebook reel here. And don't worry about all of this. We'll go through all of this, explain it, and you'll have the chance to build it yourself as well. So I'll just make sure that you guys have access to it. And if you don't, I'll just drop this in the chat again. All right, cool. So now we're in the code base. And basically what we'll be trying to do is to train an AI that can take a handwritten digit as an input and output what number that handwritten digit actually represents. Now, this is an interactive lesson, and thanks to Google Colab, you can all follow along with this. So all you need to do is open up this notebook and go to File up here and click Save a Copy and Drive. Right? Because if you guys actually edit this one, then we won't be able to run anything. So please go to File and click Make a Copy, and make your own copy and follow along with what we're doing. And yeah, so I'll wait around 30 seconds for everyone to find their way to this notebook and make a copy. Cool. Is everyone done, or should we get started? It's not loading. Yep, here's the link again. It's not loading, interesting. Sorry, I'll just check the permissions again. Sometimes these things can get a little bit weird. If anyone on this internet can view, I'll just change it to commenting, that probably, okay. Does everyone have access? I think it only works with Chrome, just because it's a Google product in this case, but yeah. Interesting. Is it not loading for a lot of people or just a couple? Oh yeah, that's true. If you're on a school account, it won't work. So just make sure that you're on personal, because school accounts don't let you join Colab notebooks and everything. Okay. Is everyone on their personal accounts and accessing this? Because if you are, it should be working. Interesting. Okay, that's interesting. I think it might have to do with the Chrome version itself, as opposed to it, because it's shared with, as you can see, anyone on the internet with this link can comment. So yeah. Yeah, so don't worry about it if you can't access this yet. because what we will do is that we will send the completed version of this file. So as you can see, there's some to-dos here, and we'll send the completed version of this file at the end of this workshop as well. So even if you guys don't have it, don't worry, because everything will be there. How do I put it on dark mode? Spoken like a true programmer. Yeah, I think it's in view, probably. No, it's in settings somewhere. But yeah, I did it once and I never thought about it again. Oh no, sorry, it's right here. Settings, and then just team dark for dark mode fanatics out there. All right, cool. So let's get started. Okay, so first thing first, we actually need to import some libraries. Now, in the presentation, I mentioned how there are really complicated algorithms like gradient descent that help us update our perceptrons thousands and thousands of times until we get a pretty good model. However, thanks to libraries such as Tensorflow, that is no longer needed. Now, all you need to do is pre-process the data, build the model, and specify the input and output data. So pretty simple compared to the stuff we went through in the presentation. Now, first things first, for those of you who have access to this and want to follow along, just click the run button over here, or just do Control Enter, and it will run that particular cell. Now, first things first is that we actually need data. Now, all we need to do here is we need some sort of database, right? And we need a database that has all of the inputs and the outputs, the image and the actual number that that image represents, so that our AI can understand the relationship between those two things. So let's quickly run this file, and we'll be using the MNIST dataset for those of you who are familiar with this. So this is a default dataset that's provided by Keras and TensorFlow. So here you'll see we've printed out a sample from that dataset. And this is exactly what I was talking about. So the actual image here is a 5, right? But we need to convert this in some way to numbers, because otherwise we can't pass it into the neural network. So what our library has done for us already is convert it for us. So as you can see, the 0 is all the background, right? So the 0 represents the background. And the parts that are numbers, like 253, 212, etc., that represents the actual number itself. And if you look at it, this kind of looks like a 5 already, right? Even if you just look at the numbers. So what will end up happening is that we will turn this huge grid of numbers into a simple list and pass it into our network. Perfect. So right now you might notice that the image size is 28 by 28, right? So what happens is that this means that there are 784 total pixels in this image. And what we're going to be doing is converting it from grid form into a long list. And that's really what we've done here. So as you look at it, we have training and testing data. Training data is to train the model, testing data is to test it and evaluate its performance. Pretty simple. So we can see that before we pre-process the data, the shape is 60,000, 28 by 28. 60,000 is the number of data samples we have, right? Number of data points, basically, number of images. So first it's 28 by 28, and that's because we haven't really pre-processed it. Then we use the reshape function, and we convert it into 784. So now we've gone from a grid to a row of 784 pixels. Now this has a lot of benefits. First is that you can actually pass it in through the neural network, but some neural networks also don't need to do that. That's a story for another day. But the second more important benefit is that it allows our data to be processed faster and the network to train faster as well. Because since we only have one row, the neural network doesn't need to process things parallelly, right? And we'll get into that more later on if you guys are interested. But TLDR is that doing this makes our network run much faster. All right, cool. Now what we're going to be doing is actually writing some code and building the model. Now, the way this works is through something called a sequential library, right? What we basically need to do is first define the model, right? And TensorFlow actually has a really helpful library called Sequential that'll help us to accomplish this. So for those of you following along, just type what I typed and we'll explain it and run through it together. So first, that sequential, and this just defines our model, right? And what we need to do is define our input size, right? And this basically tells our model that, hey, this is the size of the first layer of the neural network, right? And we want to specify input size to 784 because that's what it is. But also add a comma at the end. And this is just so that it can add the number of samples that we have. Because you might have 5 samples, 10, 20,000, 30,000. So this comma just tells the network that it can add that in, right? And iterate itself a number of times. Cool. So, is everyone understanding? Everyone's done with that, and can we move on? Mhm. Yeah, cool. So I'll just wait for a second. Yeah, so all you need to do is just run these cells. So click the play buttons on these ones, and just see the output. Look at the code if you want, and run all the cells. And then once you get to the to do parts, that's where we type it together. Oh, I think someone might be editing this because I just typed it in and it's not there. Sorry, let me just go back real quick. So far, this is all we've done. Right, we've done model equals tf.keras.models, sequential, which is the model library, and we've specified the input size. Cool. Let's keep going. Our call ends in 7 minutes, and that's all good because this shouldn't take that long. So the Keras model is just a variable, right? That's all it is. It's pretty simple. It's just a model object. So the library basically offers a way for you to build models, and that's all it is. Cool. So let's continue on real quick. Yeah, it's basically doing it behind the scenes. So now let's start adding the model layers, right? First, we want our input layer. So this is pretty simple. Just use model.add. And for a regular neural network, you would use something called a dense layer. And later on in the stock prediction workshop, we'll discuss how there are different types of layers as well. But for now, we're just going to be using dense. So let's make the size of this first layer 300 because why not? And this is the kind of problem with neural networks is that you can specify the layers to any size. So sometimes it's almost like trial and error trying to get the right sizes, right? So 300, and we'll set our input shape to the input size. Input size. Cool. So that is our first layer. And now we'll just add another layer to this as well. And in total, it depends on how many layers you really want. You can experiment with more or less, but typically you want to have around 3 to 5 layers. That's usually the optimal size, unless what you're doing is really simple. And now we're going to specify an activation function. Now, activation functions are pretty simple. They just kind of restrict the outputs of the perceptrons, right? Because sometimes perceptrons will output negative values, but in this case, we only want numbers that are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Because it's a classification problem. So if we have like -5 as the output, that doesn't make sense. So there's this really neat function called ReLU, and what that does is that it takes all negative values and just sets them to 0, and all positive values and just keeps them as them is. So basically it gets rid of negative values. Cool. Next, we'll be adding a quick dropout layer. And dropout is really interesting. So think of dropout almost like a teacher giving you a different test, right? So what usually happens is that if the neural network is training on the same data for a really long amount of time, it starts to memorize the data. It starts to know that, okay, this is this sample, so this is the answer. Almost like a student that's cheating on a test, right? So it doesn't actually have any clue what it's doing. And that's why dropout is important. What dropout does is that it shuts parts of the network down so that other parts of the network can be tested. So this way, it forces the neural network to actually learn something instead of just, memorizing the data set and cheating on the test. So dropout is like giving your students a different test. And you can set a probability of this happening, and usually we just set that around 0.2. Cool. Next, we're just going to add a couple more dense layers. So this is pretty simple. You can just copy paste this and just change the layer size to what we're doing. So we're going to add one more. And what you typically want to do is that you want to make the layer size smaller and smaller as you keep going down, right? So this is going to be 150. This is going to be just 50. And the final one is going to be 10, right? Remember that we have 10 output values, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we want it to output one of those 10. So that's why the output's going to be 10, right? And we'll change this function to softmax. And softmax is a function that particularly deals with classification. So it turns all those random numbers into probabilities, right? It's a little bit more complicated than we'd like to get into, but just remember that it's meant specifically for classifying problems, right? And at the end of this all, We just type in model.summary to signal that we're done building the model, and we run the cell. And we should see an output something like this. And oh my god, we have 333,000 parameters.
Hey,
Right? So you can get
Aditya,
pretty large. And you can probably see.
sorry to interrupt. I just want to say, can we get a quick time check?
Oh, yeah, sure. Yeah, it says the call will end in 3 minutes.
Yeah, so we'll ride that out, and then I guess they have a break.
Yeah,
okay.
Absolutely. Cool. Yeah, so we're almost done here. So 333,000 parameters. That's a lot. So yeah, now what this does is that it just compiles the model, right? So there is something called Atom in TensorFlow, and what it does is that it's kind of like gradient descent, right? But it's a different version of it that's more effective. So you don't need to worry too much about this. Just remember that it's just specifying how we will update the weights. Now, all we need to do is train the model. Now, in the interest of time, I'll just copy paste this one here because otherwise it would take a little bit too long. Yeah, but once again, I'll have this full version linked as well, so you can see. And it's actually pretty simple. It looks really complicated, but oh wait, that's the wrong one. Sorry. Oh no, someone deleted it again. Nope, never mind. Sorry. Oh, I typed in the wrong spot. Sorry about that. Okay, anyway, so here we're just going to be training the model, right? The batch size is the number of samples you want. The epochs is the number of iterations, right? Like the number of data points, basically. And then this is just fitting the model. So we're specifying our training data, our testing data, and our callbacks. And this plots the accuracy. So let's quickly check this out. And you should see that initially the accuracy is low. This is 33% accuracy, right? But as time goes on and updates are made, the accuracy improves. 33%, 67%, 81, 84, 86, 87, and it's going up and up and up. And at the end of the 25 epochs, it'll show you a graph, and it'll show you that it goes up. So, and now we've hit 93%. And here's our graph. We see that initially at epoch 0, our loss was our accuracy was low, 40%. At the end, we got 95% accuracy. So let's test this out and see what happens. And this will just put that into words for you so we can understand it. Model's accuracy and loss are 93.8%. Meet accidentally ran out of time because Google Meet decided to make everything paid, which is sad. All we need to do now is just run this last cell, and this will just print out the images and tell us the model's prediction, right? And as we can see, our model is actually pretty damn accurate. Like, look, the model prediction is 7, and this is the actual image it's referring to. 7 and 7, 2 and 2, 1 and 1, 0 and 0, 4 and 4, 1 and 1, 4 and 4 again, 9 and 9, 6. And this one is actually absolutely nuts because even I can't tell what this is. Like, it might be a 6, but it really just looks like some random gibberish, right? But the fact that the model was able to predict that this is actually a 6, that's really a testament to see that AI models might be able to pick up on trends that we ourselves can't even see. And the last prediction was 9. And that's crazy. We've just built our first AI model, trained it, seen its improved accuracy, and ultimately, we've just built our first AI model. So pat yourselves on the back, guys. This is awesome. And yeah, so I'll send the solution notebook to this so you guys can see exactly what I typed and what's been done. And yeah. Cool. So that, I think, brings our first workshop to a close. Thank you guys so much for sticking around, and I'll pass it over to Sid, who will tell us what we need to do next.
Wow, Aditya, thank you so much for that. I think we can all agree that when I say that that was a eye-opening presentation. But anyway, I really do wish that my grade 5 French teacher had access to this technology back then, because then maybe he wouldn't have failed me that one time because he couldn't read my handwriting. But I think with that, we can call it for now a break. You guys have been really working super hard for the past hour and a half. So it's around 2:23, 2:24 right now. So you guys have a 40-minute break, eat lunch, go for a walk, stretch it out, do whatever you need to do, and be back here by around 3:04, 3:05, and we'll get started with our next workshop and the next events that we have planned for you guys. So I'll see you guys in 40 minutes. Enjoy the break.